So let's do an actual example now. Here we have a fireman sliding down a pole. Now we're going to introduce another force in just a second here. But we have a fireman sliding down a pole. Now I'm going to do a very poor job of drawing this fireman again. Alright, so he's holding onto the pole right here, and he's sliding down it. Alright, and I know you're all laughing right now. And he is 9.7 kilograms. So let's write that down. Mass of the fireman equals 97 kilograms. That's about right for an average sized man. And the pole is 3.0 meters. So what kind of a measurement is that? Well, that's displacement. And so he's being displaced downward. So we could probably say that our delta y, that is our displacement, is negative 3.0 meters. Okay, he slides down to the ground floor. Starting from rest, so what does that tell us? Okay, initial velocity equals 0 meters per second. He slides with a constant acceleration. All right, so he's going faster and faster and faster down the pole, and he reaches the ground in t equals 1.2 seconds. So the question is, what was the upward force exerted by the pole on the fireman? Now, if you think about that for a second, we haven't talked about this quite just yet, but that upward force that's opposing the fireman's downward motion, you're probably thinking is friction, and you'd be right. That pole, because of friction that it creates, unless the pole is greased, in which case our fireman's in big trouble, is going to oppose an upward force. That's why you hold on to the pole, so it increases friction and it slows you down. So we have two forces really acting on our fireman right here. Let me start some other colors here. The one force is created as a function of his mass being accelerated by gravity. So I'm just going to take this point right here and pretend it's like his center of gravity point. So there's a downward force created by our fireman, or you might say acting on our fireman, and that is his weight force. And what we just said was the weight force can be described as mass times gravity, times the acceleration of gravity. Okay? Well, what we're being asked is, what is the upwards force being applied to the fireman by the pole? So the pole is kind of impeding his downward progress. The pole is kind of pushing up on him. So I'm going to draw it like that. Force pole. All right. And so that is what we're solving for right here. This, we don't know what that is. But he slides downward with a constant acceleration. Excuse me here a minute. We don't know what that acceleration is quite just yet, but we can find that. So right here, we've summed up all the forces that our fireman is experiencing. There's only two forces. One force is pulling him downwards to earth. What is that? It's the force created by gravity. We call that, oop, I lost my blue color. We call that the weight force, Fw. And we know that that is equal to mg, his mass times the acceleration of gravity. G doesn't change. G is always 9.81. The force created by the pole upwards, we don't know what that is. All right? So we know that for this whole system right here, if we take the whole fireman, all these forces here, the downward force because of gravity, the upward force because of the pole, and if we add them all up and we get the force that all, when we sum all the forces up, that's what I'm looking for, we get a net force on this whole system, right? In red, I'm going to write the net force. The net force, whatever that is, when we have that downward gravity versus the upwards friction, that's going to give us the mass involved, that is the mass of the fireman, times the acceleration that that system, or this, in this case, this person, is experiencing. So the net force, you might say, on the fireman is the mass of him times the acceleration. Now, we don't know his acceleration, but we can find it because, oops, I don't want to do that. Look at what we have here. We've got displacement, we have initial velocity, we have time. We should be able to solve for acceleration, right? Because displacement is initial velocity times time plus 1/2 times acceleration times time squared. So we're given all those parameters. We don't have acceleration. We can solve for acceleration. You might say acceleration of the fireman because we're told all about him right over here. We can say that that is 2 times the y displacement. This goes away, right? Because initial velocity is 0. Divided by time squared. Divided by time squared. All right, let's plug in what we have. 2 times our displacement. So our displacement is negative 3.0 meters divided by 1.2 seconds. That value squared. I have this written down here somewhere. I get is 4.16 meters per second. That's the acceleration now of the whole fireman system. That's that right there. That's the acceleration of the fireman. So we can write the net force on the fireman 2 different ways. And what I'm about to do, I think I touched on a little bit earlier in previous videos, but this is going to be really important. We can say Newton's second law can tell us that, or tells us that the net force on this fireman is his mass times his acceleration, which we just found. Okay, we know that. That's great. It is also just as true to say this. The net force, let's change to black here. No, I'm going to keep it red. The net force on the fireman is also equal to the sum of all the forces when you add them up. So let's pretend that this is this is the positive direction up here. This is the negative direction down here. So we can say that the net force on the fireman is force from the pole minus the force due to gravity. Oh, you know what? I'm gonna be notating gravity a couple different ways. The weight a couple different ways. I wrote it as FW, didn't I? I sometimes write it as FW. Sometimes I write it as FG, force due to gravity. I think I did that on the previous slide. Yep, FG. I do that. I write FW sometimes. Sorry about that. Don't mean to confuse you, but that is the weight force. So, just to keep us consistent here, let's back that up. The net force on the fireman is the pole upwards minus the downwards weight force caused by his weight being accelerated by Earth's gravity. So, what we can say then is that since both of these equations equal net force, that means they're both equal to each other. It's like writing the same thing 2 different ways. It's like the transitive property, sort of. If A equals B and B equals C, then A equals C. So what we can do is say this. Since all this equals this down here, the mass of the fireman times the acceleration of the fireman equals the pole force, pole, minus the weight force. All right? Or you might say the difference is the the difference between the pole and the weight force is his actual mass times his actual acceleration. So let's solve for the pole force. Oh, and you know what I did not do? I forgot to put a minus sign right here, didn't I? Shame on me, shame on me. Our acceleration is actually negative, isn't it? That would have thrown everything off, wouldn't it have? So let's solve for our pole force. That is the force the pole is exerting upwards on the fireman, causing him to accelerate slower than he should, because we don't want him to fall straight to the floor. We want him to accelerate down at a safe rate. So the pole force from the pole, caused by friction really, is going to be the mass of the fireman times the acceleration of the fireman plus his weight force. Okay? Plus his weight force, which is really mg. Force of the pole equals 97 kilograms times negative 4.16 meters per second squared. I didn't even do that. I didn't even put a square there. I'm losing it. Meters per second squared is acceleration plus the weight force. Now think back for a minute. How do we get the weight force? Well, we take just simply the mass times the acceleration of gravity, g. So 97 kilograms times 9.81 meters per second squared. That's like saying, if we factor out the 97 kilograms, 97 kilograms times negative 4.16 meters per second squared plus 9.81 meters per second squared. I'm always running out of space, aren't I? Goodness. So what is the actual force that the pole is applying upwards to the fireman to get him to fall at a safe acceleration, not to fall straight down to the floor? 97 times negative 4.16 plus 9.81 equals 548 newtons. 548 newtons. That's what I get. That's the upward force that the friction from the pole is actually applying to the fireman. Sorry that got a little messy right there, but the big thing you want to take away from this, the big thing you want to take away is this. And I'm going to box that off in orange right there. Write the net force on an object two different ways. Write it as a whole system. That is the mass of the whole system times the acceleration of the whole system. Also write it as the sum of all forces, all summed up. So the positive forces plus the negative forces, add them all up. Since both of those equal the net force, they can be set equal to each other. And you can solve for either the acceleration or the force or even the mass of an object that way. This is big, this boxed off area right here, writing the net force two different ways. Well, I hope that helps. We're going to be doing some more equations like that, or well, more problems like that in future videos. But if you have any questions, please give me an email and let me know. But for now, thanks for tuning in, and I'll catch you later.